right, so today is lesson 6.4. We are doing more with vectors, but we're doing vectors with dot products. One of the things I do want you to take out is your notes, boys, your notes from 6-3. Because I'm going to show you something towards the end of this. So if you will find your 6-3 notes, just so you have it handy. And a highlighter might be useful. All right, so today we're going to use something called the dot product. A dot product is just another tool with vectors. It's just another vector operation like adding vectors, subtracting vectors, using scalar multiplication. But the difference between a dot product and adding, subtracting, or multiplying with a scalar, all of those gave us another vector, right? But when we get what's called a dot product, the dot product will give us a scalar answer and not a vector. And a scalar answer would be just like a number.
So if we see like a dot, we can't assume it's like regular multiplication?
It is regular multiplication. The dot product involves multiplication, but the result of a dot product is a scalar, a number, not a vector. So yes, the dot still means multiplication. And so here's your definition of a dot product. So if you have a scalar u and a scalar v, a vector u and a vector v, then their dot product, which means to multiply them together, looks like this. So you're going to multiply the x values of the u and v vectors together. Then you'll multiply the y values of the u and v vectors together, and then add that sum together for a final number. And we'll do it with real numbers here in a minute. And so you're not going to end up with a vector. You just get a number. It doesn't mean the magnitude or anything like that. It's just called the dot product. And we use it to do other things, and I'll show you that in a minute. Here's other properties of dot products. So that's going to be important to know. In fact, you might want to just kind of highlight all that there. We've got the commutative property, which means that you can multiply in whatever order you want to. You can multiply the first vector to the second or the second to the third. It doesn't matter the order that they're in. If you multiply 0 to any vector, you should end up with 0. That's kind of like from yesterday. We can distribute. So if we have a vector times the sum of two vectors, all you have to do is do u times v, which is a dot product, and then u times w, which is a dot product. So you do two different dot products, and then you would add those two numbers together. Because remember, a dot product is going to give you a scalar, a number, and not vectors. And then this is scalar multiplication, where you have a number times a dot product. So all this is saying is that you could multiply the c to the vector itself like we did yesterday. So multiply that number to the x and y value of that vector, and then take that new scalar vector and multiply it with the dot product to the other vector. Or you could just multiply right here, as you see, the dot product, and then multiply that number to that dot product. And then here we have what happens if you square two vectors. You're going to find out that it's the magnitude squared. And so let's go ahead and go through some questions. So let's look at what exactly a dot product is. So I'm going to use black and red just so you see my different forms. And I'm going to call this vector u and vector v. You don't have to write that down there, but just for your knowledge. So for my dot product, I'm going to take my 4 times my 2. And then I'm going to add, let's get the right color. I'm going to add to that the product of the y's, so 5 times 3. So I get 8 plus 15. What does that give you? So my dot product of those two vectors, which are in component form, is just 23. So you see how I get a number and not a vector.
So wait, is it called a dot product or a scalar?
It's a dot product. My result of my dot product is a scalar.
So the answer is a scalar, but this
correct.
Itself is a
because your scalar, remember, is just a number. It's an integer. And well, because this is in component form, right? Yeah. See how you have the little v parentheses? So I know that this is a vector in component form. If I were to add the vectors together, like we did before, wouldn't you get 6, 8, and you would still use the v's? Yeah. So if I add the vectors together, I get vector component form, and so the answer is a vector. right?
Yeah.
But if I multiply the vectors together, which is called your dot product, I don't actually get a vector, I get a number, and we call that number a scalar, right? So we no longer have a vector. Is everybody clear as to that difference? All right, so then look at B. Go ahead and try that on your own. Now you have a negative this time, so focus on the sign too. Did you get 0? Okay. So your scalar turns out to be 0. And then try that one. Did you get -6? So sometimes you get a positive, a negative, sometimes you get 0. And then, of course, if any of these happen to be fractions in here, you might end up with a fraction as an answer, or it could be a decimal. Normally, you're going to have integers that are in your vector component form, but there's nothing that says it couldn't be a fraction. All right, so then let's look at some properties here. They've got vector u is 4, 3, and vector v is 5, 2. And so we've got a dot product here times another vector. So some of you, if you want to, you can multiply those two together first, and then times the v again, or you can multiply v times itself, and then multiply it by u, right? So it could be done either way. It doesn't matter. So I'm going to just do what they've asked. So I'm going to take u times v. So multiply 4 times 5 and 3 times 2, and we're going to add those together. And so you might want to put off here to the side because we're going to do these in pieces. It's really hard to try to do it all at once. So my u times v is equal to this. So don't I get 20 plus 6 is 26? So I'm going to take that. Now it's a scalar, right? So really what I'm doing now, so this is step 1. For step 2, I'm going to take 26 and I'm going to multiply it to v. Which would be 26 times 5, 2. And so I get 5 times 6 is 30, 5 times 2 is 10, 130, comma, and then 52. Now, doesn't my answer have an x and a y to it? So the answer to this, to multiplying 3 vectors together, actually gave me a vector, didn't it? If I multiply 4, I probably will have a scalar, right? All right, so let's try 2u times v. So I've got scalar multiplication with a dot product. Now you have a choice here. I'm trying to get this up higher. I don't know why it won't go. Oh, there goes my thank you. So you have a choice. You could do u times v, and then that'll give you a scalar, and then you can just multiply that scalar by 2. Or you can multiply 2 into the u. I'm going to go ahead and do it that way because that's what they've got there. So 2u would be 2 times 4 comma 3, which gives me 8 comma 6, right? Then I'm going to take that and multiply it to v. So then 2u times v would equal, so now I'm looking at these two vectors right here. So I'm going to take 5 times 8, and then the y's are 2 times 6, and then I'm adding those together. And so I get 40 plus 12, which is 52. So remember our dot product from before? Before when we did u times v, right here, didn't we get 26? right? Isn't u times v 26? What's 26 times 2? 52. So would it have mattered what order that I multiplied in? No. All right, so then look at C. What does that notation mean? A magnitude, minus 3. So we're going to have to find the magnitude of u. So isn't the shortcut to finding the magnitude of u square root, and then don't I take the x value and square it, and the y value and square it? So then I get the square root of 16 plus 9, which equals 25, square root of 25. That's lovely. Doing a real good job there. And what's the square root of 25? 5. So then magnitude of u minus 3 is equal to 5 minus 3, which is what? 2. Now there's one more I want to add on here. Yes?
But I think you just do like e squared minus 3, then substitute.
But that's not the original problem. The original problem is not magnitude squared.
But isn't v times v magnitude? Oh, the magnitude squared. Okay.
So we have a square root in there then, right?
Yeah.
Okay, so then remember one of these right here, so let's kind of talk about what Michael was asking about. See this one here where if you take a vector times itself, you get the magnitude squared? Let's see what that looks like. So turn your paper to the side because that's where we have some room. There's stuff on the back here, so we can't exactly flip it over to the back. So here's what I want you to add. So this is an addition to example 2. So this is example 2. And we're going to call it D. And then let's say that U is still 4, 3. And I want you to find the magnitude of U squared. So according to this over here, isn't the magnitude of a vector squared equal to the vector times itself? Okay, so that must mean that all I have to do is do u times u. So I have to take u times itself. So I end up with 4 squared, right? Because u times u, both the x and the y are going to be the same value. So 4 squared and 3 squared, and don't I add that together? So I get 16 plus 9, which is 25. So I go back to, because we just found the magnitude of u earlier, didn't we? So over here, the magnitude of u was 5. What's 5 squared? 25. And isn't that what we just got here? So the magnitude squared should be 25, which is exactly what the vector times itself turned out to be. Okay? All right, then one other thing. So let's call this E for Edward. You're going to have to really squeeze it in here. So here's E. The dot product of U with itself is 6. Now I want you to realize, and so you need to write this in here, that I'm not talking about the same u as what we just did up here. So this is a totally different vector u. So I want you to write in here, this is not the same u vector as above. And for anybody printing out the notes, I've changed this value here to 6, just so that there was less confusion. All right, so what it says is the dot product of u with itself is 6. Well, doesn't that mean that the dot product of u with itself is 6? Doesn't that mean then that the magnitude of u squared is equal to 6? Because if the dot product of u to itself is the magnitude squared, then doesn't the magnitude squared equal 6? Does that make sense how I jumped to that conclusion? And so then what would the magnitude be here for this particular vector? square root of 6, because wouldn't I take the square root of both sides to solve for just the plain magnitude? So then that goes to reason that the magnitude of u is equal to the square root of 6. So if you're ever given this verbiage, the dot product of u with itself is 6, think, oh, that's u times u. That means that it's the magnitude of u squared. So replace that equals 6. Now you can easily find the magnitude by taking the square root. Mike? What? No, not in this case. Good question, though. You want to know if we have to do plus or minus? Not in this case. We're not going to have a negative length, right? Just remember, magnitude is length, so we won't have it negative. Okay, so let's flip it to the back. And let's look at some applications of why are we even learning the dot product. And I've had some very interesting discussions with my other pre-calc teachers. Regarding this next question. All right, so right here, the angle between two vectors. That's why I asked you to take out your 6-3 notes. Didn't we find the angle between two vectors on the notes there? The very last question on the back of it, right? Can I see somebody's real quick? Because I left mine at home. All right, so remember this problem here on 6-3? Such lovely writing. We found, using reference angles, this angle and this angle, we added them together, right? So that's how we found the angle between two vectors. We can also, thank you, do that with dot products. And I'm going to do that same problem here again in a minute, but we're going to use the dot product and see do we get the same answer. If we do, then they must both be viable ways to solve that problem. So here's the formula.
So whichever way that we find
Unless I ask you to use dot products. So you want to know, whichever way is easier. But use the way that you're told. If not, you can use whichever way you like best. The way I taught you in 6-3 is easier to remember. There's not a formula to it, but sometimes you can't always use that in certain situations. So here we've got the cosine of theta, and it says here that theta is between two non-zero vectors. Meaning, if one of the vectors has a magnitude of 0, won't it make the denominator 0 here? Yeah. That's the only reason why it's saying that. So your angles between two vectors, you're going to take the dot product of the vectors, divide that by each of the vectors' magnitudes, so that'll give you some number or some decimal. And then how do we find theta if we don't know theta? Inverse cosine of whatever this turns out to be. So that's what we're going to do. So we're going to draw a picture of what's going on here. So I'm going to draw a lovely straight line. And all of this is in the first quadrant, correct? So make your axes mostly in the first quadrant. So the first thing I'm going to do is plot my vectors. So I'm going to start off with 4, 3. Because it's in component form, I know that it goes from 0, 0 to 4, 3. And then the next one is 3, 5. And it's also in component form. So wouldn't theta be the angle in between those two? Now, could I still do this the way I taught you in 6-3? Sort of. What would I have to do instead? I would subtract the angles, because I would make a right triangle this way for the pink one, right? And I would find the angle from here to here, because it's always from the 0 axis. And then for the purple one, I would find my reference angle would be here from here to here, and I would have to subtract the two. So here's a situation where I would subtract those. So that's still doable, but we'd most likely be using our tangent, right? So then here, let's go ahead and use our dot product. So let's find the dot product between these two. So we're going to do cosine of theta is equal to, multiply your x's, so 4 times 3 is 12, plus multiply your y's, 3 times 5 is 15, all divided by, and then we have to find the magnitude. Square root of, magnitude of u is 4 squared plus 3 squared times the magnitude of v is 3 squared plus 5 squared. Anybody not sure where I got any of that? Mike. Okay, so I'm using this formula up here, right? Okay, so cosine of theta, because I'm trying to find that right there. The dot product, remember, is just the x's multiplied together. 4 and 3 is 12. Okay, so the denominator, remember, your magnitude. To find your magnitude, don't you take your component form and square the x, square the y, and take the square root? That's what I'm doing there. Squaring x and y, x and y. And then let's go ahead and simplify. I'm going to go out here to the right. So 12 and 15 is 27 over 4 squared is 16 and 3 squared is 9. 16 and 9 is 25. Square root of 25 is 5. So I have 5 times. And then 3 squared is 9. 5 squared is 25. What's 9 plus 25? 34. Can you simplify the square root of 34? No, because it's 2 times 17, right? Then I can't reduce anything here, and it's not necessarily needed to reduce it, because I've got the cosine of theta is equal to this right here. This is what I want to input into my calculator. To find theta, as you stated, don't I take the inverse cosine of, I'm going to take 27 and divide it by 5 rad 34. So you need to be really careful when you put this in your calculator, because your calculator automatically assigns a parentheses, doesn't it? So watch what I do. Number one, make sure that your calculator mode, again, I'm always checking, is in degrees. Right? So mine's in degrees, so I'm good to go. So that I'm going to hit inverse, second function, cosine. So I have my cosine to the -1, and it automatically starts with parentheses, which is fine. So we're going to take the 27 and divide it by, but then I need to use, well, sometimes I might have to use parentheses here, and in fact, just to be on the safe side, I'm going to use parentheses. Because sometimes you have 2 radicals that you're multiplying together. If you don't use parentheses in your denominator, then it's going to think that you're dividing by the one radical, but multiplying by the other one. So you want to be careful. So I've got 5 times radical 34. End your parentheses for the denominator and end your parentheses for the entire cosine. And then I can hit enter. Does that seem like a reasonable answer? Yep. So that must mean that theta is 22 point, it's approximately equal to 22.2 or 22.17. It didn't say how far out to go, so I'm going to go out to 2 decimal places. So shall we apply this same concept to our homework from yesterday? So Amber, if I could borrow that from you again. I'm just going to do the dot product real quick with this one right here. I'm going to do that up on the board. You can help me with the cosine. So my dot product, would it be 2 times 1? Cosine of theta. 2 times 1 is 2, plus 2 times -2, isn't that -4? Right? All over square root of 2 squared plus 2 squared times the square root of 1 squared plus -2 squared. So this equals -2 over 2 squared plus 2 squared is 4 plus 4 is 8, right? In your calculator, you can just write square root of 8. You don't have to simplify. Times 1 squared is 1, 2 squared is 4. Isn't that the square root of 5? So aren't you going to put into your calculator the inverse cosine of this? Tell me that you should get, on your calculator, should give you 108.43. If you plug that in. Did you? Did anybody do it? And you got it. So, yeah, she's got it. So here's her calculator, right there. Right? 108.43, did it work? So both are acceptable methods. So here's that back, here's that back. All right, let's do the last two problems. Let me erase my board. Okay, so then, all right, then we have to talk about what's called an orthogonal angle. It's a very lovely word. All it means is two vectors are orthogonal if and only if their dot product is 0, and if their dot product is 0, those angles will meet at right angles. So look at what we have to do here. Are the vectors u and v orthogonal? So all you have to do is find the dot product. 2 times 6, negative 3 times 4, and you're going to add. So I get 12 plus a negative 12, I get 0. So what's your conclusion? Yes, u and v are orthogonal. This will be on your test. You will forget what orthogonal means. Highlight that and write study, study, study. All right, then a last example 5. Vectors that are scalar multiples of each other are parallel. Determining parallel vectors. So I want you to go ahead and write this down here at the bottom. If there is a scalar, some number c, you can multiply whoops, wrong way, to vector u so it equals vector v, or vice versa, then they are parallel. Can't you just look at, first of all, you just look at the vectors. Can you multiply 3 by something to get 9? 3, right? Can you multiply 2 by 3 to get 6? Here's the easiest way to tell though, so there's that. Or just take one vector and divide it by the other vector. So if I take my vectors and divide them, I've got 3 comma 2 over 9 comma 6. Split them up, 3/9. Doesn't that give you 1/3? And 2/6, doesn't that give you 1/3? If I had flipped them and did v divided by u, wouldn't I end up with 3? If both of these are the same, then the vectors are parallel. And so, since C is 1/3 or 3, depending upon how you view it, the vectors are parallel.